Okay, so this is chapter 12. The topic is kinetics here for this. And here's what we're going to say. Let's have a chemical that we're just going to generically call A. You know, algebra people use X or whatever. And let's let chemical A, let's let it be a reactant. In fact, we'll just let it be like the main reactant or maybe the only reactant in a thing. And so there's a symbol I got to remind you of. If you have a bracket like this around A, that is like literally translated into English as the concentration of A in moles per liter. That's the concentration of A in moles per liter. You may remember that from equilibrium stuff that we did last year. We had like products over reactants and did some K expressions, and we used this bracket around a chemical quite a bit to indicate that, hey, we're talking about the molarity of it. So let me make a quick sketch graph that will simply have the concentration of A, and let's have it go against time. We're talking about rate here, the change of the concentration of A, okay? What do you think that the concentration of A, if A is a reacting chemical, what do you think this graph looks like as time goes by for the amount of A that's still in there? Goes down. As a matter of fact, it looks like this. That would be what a lot of mathematical people will refer to as like an exponential decay. And if we pick 2 points on the graph, let's say here to here, I think you would agree that the concentration of A has changed. And time has gone by. There's been a time interval. So here is a definition for you of how we would find the rate of this. And this isn't anything new to you guys. You know all about rates. The rate of a process like this is equal to the change in this concentration of A over the change in time. You know that. The rate of anything is the change of it over the change in time. So nothing new for you there. There is one little thing I got to add to this. And one other little statement. At this point right here, if we did the slope between these 2 points, you can see that it's pretty steep. There was a change in A over time, and it was a pretty steep one. If we were to go over here and do the same kind of procedure, pick another time interval, do slope of the line there between those points, it is more like that. So there are 2 things here. First of all, you can see something here. In most chemical reactions, it would appear, and if you think about it, it's probably true, that the rate decreases over time. There's one other thing that's true. What do you notice about the number value of that slope? That's kind of weird. If that slope is a measure of the rate, what kind of a sign do you have when the slope's like this? Negative. That means that if this is the change of A in the top of this is a negative number, which it is, then you would have a number that comes up with a rate that's negative. That usually bothers people. They don't like the idea that a rate could be negative. So if this is actually kind of simple, if we are using a reactant like we are here, they will automatically put a minus sign in front of that change. They will say the rate is the opposite sign of the change of A. Because if A is dropping, that's going to be a negative slope. It's going to be a negative number to that. And they don't like that very much. Okay, so one more thing here. Let's go to a new page. Let's take a specific one real quick. Let's say we have a reaction where a couple of NO2s doing a little simple thing, and it's giving up an O and it's making a couple of NOs, and that kicks off some O's, and they go together and they make an O2. So kind of a simple little sort of decomposition reaction almost, what we got going here. If I were to write the rate in terms of NO2, it's a reactant. So doing what we just said, the rate of this would equal the opposite side of the change of the concentration of NO2 over time. Yeah, okay. How would, if I wrote it using that chemical, the NO, how would it change? Like, how would the definition look different? There would be a 2 on the O, so the chemical in it would change. This has a coefficient of 2, and that has a coefficient of 2. Would you agree that just as fast as this is getting used up, that's getting made? So then the difference is that the NO is increasing. So I get to drop the negative. So in theory, the rate measured it by this chemical, if I tracked a different chemical, because you got to measure something. So if we're tracking how much chemical is there to try to keep track of the rate, I should be able to track NO, and it would be made at the same rate. Now, there is one more thing to say here. There's a graph, I'll just refer to it real quick, that is in your textbook. I'm not certain what page it's on. It's right there where we're at. I'll have to look at the page. It's got 3 different graphs on it that look kind of like this. In your textbook, this is on page 562. You can see the NO2 dropping, NO2 dropping, NO2 dropping, and it's going down. The NO is going up, going up, going up. And if you look at the slope on the green graph and the blue graph, yeah, one's negative and one's positive, but they do have about the same value of the slope, which would make sense because the one is being used up just as fast as the other one's getting made. But the oxygen in this, the O2, which is the red line, you'll notice his slope is usually not quite as steep. In fact, I'd venture to tell you it's about half. Because in order to make these all equal, you would have to double whatever the O2 is doing, because it is only getting produced at half the amount. So 2 times the change in the O2 ought to equal the same one for those others. So you do have to kind of be careful what chemical you define it in terms of, because it can slightly change the way you're measuring it. Like O2 is not being produced at the same rate as those other chemicals. So you would, if you're going to track a chemical for this, you kind of have to be careful. Well, here's the only other thing I want to say on this topic, and we can go to the last thing, actually, that we need to do today. I told you it wouldn't take long. What else could you track besides concentration of a chemical to keep track of a rate of a reaction? What is something that would change as a reaction happens that you could track? Any thoughts on that? What do you think?
Well, where did you get the 202? Is it because it's half?
It's only given at half. And so if I'm going to make it equal to all the others, I'd have to keep in the amount that I got double it.
So just double it.
Yeah, so that's what that's coming from. So what I'm saying is I could track any of these chemicals and I should be able to measure what's going on. What else could you measure besides like the concentration of the chemicals that are there? Because clearly that's going to change as the reaction goes by. But what else maybe? What's that? Energy used up or given off, either way. And they do that. They'll watch the temperature changes or whatever, and they'll see the rate of the reaction by how fast the temperature is changing. Here's one you might not think of, but you probably know it's true. Don't a lot of reactions change the pH? You could sit and track the pH maybe. To be honest, if it's something that's taking ions out of the solution, you could track the conductivity changes. So if you want to get the rate of a reaction, here's the bottom line of this first section. If you find any physical property, whether it's a chemical's amount, pH, temperature, electrical conductivity, if you can find anything that you can track that changes as the reaction goes on, then you can get a measurement of the rate. You can find some way to measure it. You just need a physical thing you can track. All right. Well, that brings us to, actually, if you're following in the book, brings us to section 2 of this. And here's a question I would simply ask real quick. Based on everything we've seen, think a little bit here. Does it appear that concentration affects rate? What do you think, based on that graph right there? Do you think the amount of concentration of A that I have as it goes off seems to be affecting the rate as time goes by? As I get less and less A, what happens to my rate? Well, what's it do? It goes down. So the answer to this question that I got up here, does it appear that concentration affects rate? It does, actually. Yeah. And sort of, I guess if I was going to say this, sort of directly in this way is what I mean. Less concentration of A means, I hate to say less, but I'm going to, slower means less rate. It doesn't go as fast. So, all right. So it's kind of a direct kind of a thing. So, can we make a law? That is there some kind of mathematical equation or model that would allow us to relate rate to concentration? And the answer is, of course there is, or I wouldn't have brought it up. Here's what they all look like. There will be a constant in it, that is the constant of proportionality. Almost every equation has one. Because if you think about it, if I stick in here the molarity of A, which I agree, they depend on each other, but moles per liter for A's units here, that's not a rate. Moles per liter is a concentration. So there's got to be something else in here to make rate equal concentration of A. It can't just equal it. And this is like a lot of equations. There'll be some kind of constant, a slope, some kind of relationship that goes in there. It'll have a number value, but it'll also have units in it that help the units work out. There's one other part to the rate law. A will have some, it'll either be linear, like with an n equals 1 up there, or there'll be some power on it. So n is what we call the order of the reaction. And it will have a number value. Usually in actual chemistry experiments, it's either a 0, a 1, or a 2. You don't usually see powers or exponents higher than that in any of these rate laws, which is what we're writing here. So n is the order. One thing about n, it can only be determined by experiment. You cannot look at the coefficients. There is no theoretical way to predict what the order n of a reaction is. There's no way to do it. It can only be determined by actual measurement. Last thing on this slide real quick. This kind of rate law, where rate is proportional to concentration, that's not the only kind of law that you can make. This one relates rate to how much stuff is there. And it's a good one, but it's not the only kind. So we have a name for this. This is called a differential rate law, is what we got. Anytime you have a rate, this rate is proportional to concentration kind of law, like this one. There's only two kinds. This is called a differential rate law. Have you all done derivatives in pre-cal at all? Fooling me? No. Well, are they doing them? Yeah. The short answer to this is the differential rate law is related to the other form, which is called the integrated rate law, and it's related by calculus. So in other words, here's what's good. If you figure one of these forms of this rate law out, like this one that looks like this, the other one, which has time in it, that's what the difference is. Instead of concentration, it's got time in it also. It has the same equation Like once you know one, you automatically know the other one, which is nice.